Alright, so our next problem says, use the Rachford-Rice equation to perform a fixed TP flash calculation for a feed of 4 moles per second benzene, 6 moles per second toluene, with the flash drum set at 393 Kelvin and 150 kilopascal. What are the compositions and flow rates of the outgoing vapor and liquid phases? So I've attached the picture of the Rachford-Rice equation that we derived previously, and so we're going to use this to calculate this problem in Python. So let's start out by what we know. So we know that the moles in our feed is going to be, the benzene plus the toluene, so it's going to be 4 plus 6. All right, so then we know our z values. So that is going to be, and we'll put these inside of an array. So we'll have an array, and so first is benzene, so that's a 0.4 mole fraction, and then toluene, which is 0.6. And that's just gotten because we have 10 total moles, and 4 divided by 10 is 0.4. So there's that. And then we have our temperature, which is known, and that is 393 Kelvin. We have our pressure, which is 150 kilopascals. Right, and then one last thing we know is our K value, because we can calculate that from the temperature and the pressure. So our K is equal to our P dot PVAP of our temperature, and then divided by our pressure. And then this value will also be inside of an array because it's calling on this array that we have made before with our benzene and then our toluene. Okay, so here are our knowns. Now let's create the function that is this equation that then we will take the root solver and solve for the flow rate in the vapor phase. So, alright, so we're going to want to define a function. We can call it RR for Rachford-Rice, and we'll want to import a vector because root solver is looking for vectors. And then we can unpack this vector into our flow rate in the vapor phase, because that is what it's going to be solving for. So that is, all right. So that's what is going to be in our vector, is going to be a guess for that. So then we're going to want to return our equation over here. So we need the NP sum. All right, so then we have, so mole fractions in the feed times ratio K minus 1, right, and then divided by, and then we'll have our B divided by our F times ratio K minus 1, and then plus 1. All right, so there we go with that. I think all our parentheses work out. All right, so then let's work on taking the root of this. So root of the Rachford-Rice equation, and then we'll need a guess, so we can guess, we're going to need our guess in a list, so let's do that. Alright, so there we go. You can see we've gotten out a value, so, and that is our value for vapor. So there's that. All right, so then we can go and calculate everything else. So we know vapor, we know feed, so we can find liquid. So liquid is going to be equal to our feed minus our vapor. And then, so we got vapor, we got liquid, then we need our mole fractions. So our mole fractions, we can use, start with this equation maybe. Alright, so x is going to be equal to F times Z divided by V times K. I guess we need to, up here, we need to put that this is V. Alright, and then, so V times K plus F minus V. So we are X. And then for Y, we can use this equation for K up here. So Y is just going to be K times X. Alright, and then we can print out all of our results so that we can see them. So we're going to run a print, and we can use F strings to print. So total moles in vapor phase that is V, and then we can print F. And here, I'm just going to copy this so I don't have to type the whole thing again. But this time we're going to want total moles in the liquid phase, and that will be equal to L. And then we can print so mole fractions in vapor phase and those are our Y's, and then copy that and paste it, but this time we want to in liquid phase, and then X. Alright, so shift enter. So you'll notice something that's a bit strange here. You can see that our total moles in the liquid phase is negative. And so what that means is that this calculation isn't really valid at this temperature and pressure. And we can see that with our plots up here that we made before. So we have our pressure at 150,000 pascals that we know, and we're at 0.4 moles, so that's here-ish. And we're at a temperature of 993 Kelvin. So if you go up to 993 Kelvin, that's like up here. So this is purely in the vapor region. The Rachford-Rice equation is really only going to work if you're inside between these two lines, because it relies on our feed splitting into a vapor and a liquid phase. If we're not in this region, we're not going to have both a vapor and a liquid. And if we're above this region, as we are in this calculation, we're going to only have vapor. And so that's why it's giving us a negative value for our liquid. That essentially means you're all in the vapor phase, and this calculation isn't going to work. But yeah, so it would work if we had, you know, a lower temperature, maybe, 390. I can try. Actually, that's still a little bit too high. So you can see there, now we have, reasonable values. Nothing's negative, and it will work. But for this calculation, we were given the values of or for this problem, we were given this temperature value, which is not in the two-phase region between these two curves, and therefore this calculation will give us a negative value. But that is how you would use the Rachford-Rice equation to calculate a problem like this.